Hello, this is video 60. I'll be talking about rotational energy, so kinetic energy, and also conservation of energy when we have an object rotating. So as you can expect, rotational kinetic energy is going to be very similar to the linear kinetic energy that we've talked about in the past, which was equal to kinetic energy is 1/2 mv squared. That was for an object moving in a straight line. So we just called it kinetic energy. Now we can call it translational kinetic energy. It just means the same thing, that it has to do with just your object moving in a straight line. So if you have an object that's rotating, well, like in this picture, this object still has motion. It's rotating counterclockwise. It has an angular velocity omega. So we know that when we have motion, we have energy. So now we'll call it rotational kinetic energy, and we're going to do our usual substitutions where the mass becomes the moment of inertia and the speed becomes the angular speed. So KER is 1/2 I omega squared, and it has units of joules like all of the energies that we talk about. This picture is also showing you that if you just look at one point on the object, that one point has that speed v, but you know that that's related to the angular speed of the object with this relationship. So just reminding you that if the speed is related to the angular speed, well, if it has some kinetic energy, it'll still have some kinetic energy that you can express in terms of omega instead of v. So what I'd like to do with this now is look at an object that is rolling, such as a bicycle. So we're just looking at one of the wheels here. When an object is rotating, it has rotational kinetic energy. But if it's rolling, then if you just imagine this bike going down the incline, well, the center point of that wheel is moving, let's say, from here all the way to here. So this center point has some velocity going to the right. So there must be some regular translational or linear kinetic energy 1/2 mv squared as well, because there's linear motion and rotation. So the total energy of a rolling object is the sum of the two types of energies. So now when we're doing conservation of energy problems, our kinetic energy, we can break it down into the sum of the translational and the rotational. In this class, when we're doing conservation of energy problems with rolling objects, we're not going to have any springs in the particular problem. So that's why I just wrote PEG for the gravitational potential energies, since there's not going to be any other types of potential energies that we talk about. So what we want to do, just to practice, is we want to write out every term to remind you what they all mean. So 1/2 mvi squared for kinetic energy initial plus 1/2 I omega initial squared plus mgy initial equals the same thing for the final quantities. 1/2 mvf squared plus 1/2 I omega final squared plus mgy final.